Hello everyone and welcome to a new discussion which is on Reynolds numbers. So, when we started discussing Darcy law, at that time we also discussed Reynolds number related with laminar flow and turbulent flow. Reynolds number may change according to the conditions. So, those details we are going to discuss under this groundwater engineering course. So, let us start. So, that why Reynolds number is there, that it is to express the relative importance of viscous forces in any flow conditions, and a number is given is which is called Reynolds number, and it is denoted with R and subscript N subscript R. This is a normal convention, but depending on the literature sometimes people use some different convention, does not matter. So, NR equal to V L upon V. So, that what we see, one is the basically here is nu and not V, but the other V is the speed of flow. So, where in this nu is the numeric viscosity of the flow, which is the first one, and the V is the speed of the flow, and L is of the characteristic length. Generally L is also denoted with uppercase L, and which is the might be the width of the flow passage. So, if Reynolds number depending on the fluid conditions, if Reynolds number remains as a low value, then most likely we will have laminar flow, and this is what we are going to discuss. So, all the above parameters which we have discussed or included in this equation, and that is NR nu L upon V, that speed of flow, L is the characteristic length and nu is the kinematic viscosity of the flow. So, all the above properties must be in consistent units. The unit of the all these properties have to be same, because NR is the ratio and therefore, it is dimensionless. This thing has to be remembered, that it is a dimensionless entity or dimensionless quantity, which because it is a ratio. So, now in case of flow in pipes, if we are considering not in a open channel or in a groundwater condition, but initially we start understanding Reynolds number, and that in case of a pipe, flow in a pipe, the L is the pipe diameter, and the transition from laminar flow to turbulent flow occurs when the Reynolds number is greater than about 2000. So, if a number is very high, then it is highly likely that the flow inside a pipe is going to be turbulent. In case of a flow in a porous medium, now we are talking about an aquifer or flow through rocks or some geological formations. So, in case of a flow in a porous medium, the apparent velocity, that is q upon A, is used for nu, and the average diameter of the particles of rocks, for example, sand grains etc., is used for L. So, here the turbulences will occur when NR is more than 100. Now, here we have in a pipe system, it was from laminar to turbulent when NR number is 2000, but here in a porous medium, when NR number is less than 10, then the flow the Darcy law will be applicable, and also the flow would be laminar. As we have discussed while discussing Darcy law in 3 videos, that Darcy law is only applicable when flow is laminar, and so we can say that Darcy law is only applicable in a porous medium if NR or Reynolds number is less than 10. So, however, in a most natural groundwater flow conditions, we do not reach to that number, generally it is less than 1. So, if heavy pumping is not being done, then this Reynolds number will remain at a very low value, and most likely we will have a laminar flow inside a well. So, Darcy law is therefore valid only for laminar flow, which I have just mentioned, and may become invalid if flow speeds that are at the upper end of the laminar flow range. So, if it goes beyond 10 in case of a aquifer conditions or in a geological formations, then the flow is going to be turbulent. So, all these higher speeds, the flow rate may become proportional not to head difference, but to the square root of the head difference, and that will be the Q, that is discharge, equal to under root H and L. L is larger here. So, the Darcy law is applicable to most of the flows of groundwater found in nature, because as we have said that in general the Reynolds number for groundwater flow is generally less than 1, but because of heavy pumping it may go little higher, but if it goes beyond 10 then we will encounter the turbulent flow. So, higher flow speed that occur immediately around the well and which will frequently result in head losses and which increase is a square relationship. So, what is that head loss is that the drawdown which we will be discussing in later videos, but anyway here I can introduce in a very brief manner that the head loss that is a cone, and the apex of the cone at the water level of within the well. So, if this cone, if it becomes very sharp, then head loss is very high. If this cone remains very shallow, then the head loss is less. So, in high pumping or high withdrawal of water from a well, which will induce the this head loss, and then the relationship will increase to a square relationship, and that will be a bad from the life or health of the well. So, all the time it is the intention should always be remain in case of installing pumps and withdrawing water, that the flow should remain all the time laminar and Reynolds number should be less than 1. So, if the well discharge Q is doubled, suppose in case instead of a less powerful pump we have doubled the power of the pump, the head loss over this part of the flow path must be increased 4 times, because it is a square root. So, here you can see this cone of depression which is very shallow in that sense, and the flow may remain laminar, but the flow generally is very slow towards the well in a real situations. So, this explains why the yield depression curve, which is also known as the drawdown, that increases faster than the well discharge. So, this cone of depression, if it becomes very sharp, then the head loss is more, the withdrawal or the Q discharge will reduce, and your well may get damaged because of turbulent flow in this. So, it is also explained why the designers of a well must do all he or she can do to keep the speed of water as low as possible as it enters the well. So, this is really very important, whatever the formations are there, whether it is hard rock like granitic terrain or sedimentary rocks like sandstone, that the speed of withdrawal, the Q should be kept at the optimum. I would not say minimum, but it should be kept at the optimum, so that Reynolds number does not increase and flow remains laminar towards the well, and therefore, the life of the well, health of the well would be much longer. So, when complication arises in case of unconfined aquifers, because this piezometer. So, in this case of unconfined aquifer, you can see this cone of depression which is like this, you can see. So, if a withdrawal is very fast or Q you double, then this cone of depression may go very sharp like this, and then this water table will also go down, and that creates problems in the. So, we try to understand all this through equations, that Q is the discharge here, K2 pi v is the constant which is this part, and L1 is the hydraulic gradient of radius R1. So, R1 is here, and second the hydraulic gradient of radius R2 which is here. So, from where this R1 is coming, because it is a cone. So, the first R is coming, and this is R1 and this might be R2 here. So, these two values are there. So, let us go back again, Q equal to K2 pi R1 B1, and Q equal to K2 pi R2 B and I2. So, these hydraulic gradient at radius R1 and R2 are there, and accordingly we are handling this situation about Reynolds numbers. So, the water table is lowered in case of cone of depression, as you can see here, and so the saturated thickness B is reduced, and that will create. So, this might go in a unconfined aquifer conditions, that might go lower and your B will be reduced accordingly. So, we can write these equations where since R2 is greater than R1, R2 is greater than, because this radius is larger, then the I1 must be greater than I2 by a proportionate amount, and this hydraulic gradient, in order for equation to balance and Q to remain unchanged. So, that is why what we are trying to say through these equations, or trying to understand, that if we maintain the Q, then these things will be valid, and your Darcy law will be applicable, Reynolds number will remain same, flow would be laminar. So, as the hydraulic gradient becomes steeper, that means more water is being withdrawn than the water which is approaching towards the well, which is less. So, the water table in the center of cone of depression, which is this part, is lowered more, and therefore, this cone of depression becomes more sharper, deeper, and decreasing B is still further, therefore, L must be increased again, which is we have to manage this thing. So, vertical flow components and hydraulic gradient also come into effect. Now, if it is going down, then this vertical flow components will also play important role. So, these effects about the changes will reinforce each other, and this makes predicting the behavior of wells in unconfined aquifer more difficult, because the water table is also going down and at a rapid faster speed than in confined aquifer. So, it is more difficult to predict or understand the behavior when the pumping is going on than the behavior of those in confined aquifers. So, relatively in confined aquifers, this kind of understanding is easier than in unconfined aquifer conditions, because in unconfined aquifer conditions, the saturated thickness, like in this example, this is confined. So, saturated thickness remains almost same, and therefore, these values will also have same. So, head loss which we are considering here, that is the distance between the pumping water level and the static or rest water level. So, this part we are talking is, this is what we are saying, head loss. So, head is called the drawdown, which you have seen that these kind of cones which you are observing here. So, the part of the drawdown that results from water flowing through the aquifer to the well is called the aquifer loss. So, within this thing, and this, if I consider a solid cone, then this is what is the aquifer loss. Now, if we take out water for some time and then stop pumping, slowly and this cone of depression, depending on the geologic conditions, may disappear, and the water table will go again to the normal condition, or maybe little lower. Then we start again pumping. But if we do continuously pumping, then this becomes deeper and deeper, and this level head loss becomes much more. So, that will bring higher Reynolds number, that will bring turbulent flow and damage to the well. So, that is why, as earlier also mentioned in previous videos, that the withdrawal of water has to be very judiciously done, in a optimum manner, that drawdown does not go very deep, and there should be some time so that it settles, the drawdown disappears, and then you start again withdrawing water. That is the best practice, should be followed, not continuously withdrawing water, otherwise there will be problems in the well. So, that part of water which actually flow into the well occurs across the well for phase is called the well loss, which we have already discussed. This is the well loss which is coming. So, well loss would be this much, or head loss is almost same. So, these head losses are important, because in order to lift the water to the ground surface, the pump must impart energy to the water. That means, say, if we did not have the drawdown and the water table was here, then we will be requiring less energy to pump the water. But the drawdown has gone down, then this much more lifting of water will be required, and hence more energy is required, more electricity would be required. So, it is not always worth to go like this. And greater the drawdown, the more energy is needed, and energy that is we know is not free. Somebody will be paying, if government is giving free to the farmers, then somebody will be paying for that. So, it is anyway it is not free. So, that is why it is better to switch off pump for some time, and then after, depending on the geological conditions. So, one can estimate all these things, so that one would know that how much time it would take to things settle. That means the drawdown should appear or the cone disappears, say 2 hours, 5 hours, or maybe overnight. So, generally it is done. There is another practice which is followed in villages, that generally the water is withdrawn in the morning time, very early morning. Why? Very simple reason is that you are giving whole night for this cone of depression to disappear, and therefore the less energy will be required, because the water level or water table would be at a shallow depth relatively, there will not be any cone of depression. So, you would withdraw the water, leave the well for entire daytime, again in the evening you can withdraw. So, roughly 12 hours you are giving in that manner. But again I am saying depending on geologic conditions. If it is hard rock terrain, then the 12 hours practice is the best. If it is a Indo-Gangetic plain like situation, then maybe few hours might be sufficient. So, therefore, it is essential to that the well should be as efficient as possible, and efficient would be, that means here the drawdown should remain very minimum. So, mean drawdown should be kept to a minimum, and a useful way of assessing the behavior of a well is to do pumping well at different rates and measure the drawdown at each rate, and that is called pumping test. So, there are methods by which we can test a well, that how much water I can withdraw, and that can be done very easily by pumping the water at different rates and measure the drawdown at each rate. So, we would know that what is the speed of drawdown, if you wish to say. So, there are the resulting pairs of figures are then plotted in the form of a yield versus drawdown. So, here on the what you are seeing here on the y axis is the drawdown, here is shown in meters, and yield or well discharge here. So, see that yield depression curve, this one is, and Darcy law says that the drawdown should be kept something like this. So, if we are going like this, yeah, we are withdrawing more water than a well can provide, and therefore, this curve should not be very sharp. So, at different time, different drawdowns, it has been measured. So, these dots are there. So, these pairs of figures are then becomes useful to see that how the drawdown is happening with the time, and these curves are also called yield drawdown curves. So, like another parameter which we have discussed, this is specific capacity, beside being an index of transmissivity, also serve as a parameter of yielding capacity of aquifer of wells. So, how much water a well or a formations can hold, which is indirectly an index of transmissivity. So, we can see how this yield factor and these are related. So, as you can see that the capacity is denoted by a yield factor or a specific capacity index. So, here the specific capacity divided by the thickness of aquifer is screened. Screened means if there is a well, so the top part of the well you might be having completely pipes which does not allow water to go, but here you might be having screens. So, that is the thickness which is counted, what is that screen part. So, thickness of this screen, aquifer screen, which is what will be here. So, yield factor is a ratio between specific capacity by thickness of aquifer that is screened, from where the water can enter in the well. So, this yield factor in different conditions will have different arrangements or different possibilities. So, in confined aquifers, that is provided the pumping water level is above the top of the aquifer, to have the saturated thickness and transmissivities are constant in confined aquifer conditions. The yield depression curve should be in theory as a straight line, as mentioned here earlier also. Then Darcy law will be followed. So, as per the Darcy law, and the flow is proportional to the hydraulic gradient. Now, here as repeatedly I am saying that if a withdrawal is more, then for that time the Darcy law may not be applicable, and all your estimates may go bad or wild. So, it is always that we should maintain that this yield drawdown curve in this one, and the line should be straight. So, in practice the relationship is more likely to be curve, and that is might be a problem, because it is many times it is not very easy to maintain a straight line, so that it follows that one. So, here we ends this discussion about Reynolds numbers. Thank you very much.